Okay, so I hope my screen is visible and I'm audible. So I'll wait for 2 more minutes. Sorry for the delay from my end today. I'll wait for 2 more minutes, then we can start by 6:10. Okay. So so just to reiterate, I hope I'm audible, and moreover, uh, again, welcome back to week 4 of the problem solving session for the Introduction to Fluid Mechanics course. And in this week, we will be discussing about the forces or hydrostatic forces on flat surfaces and curved surfaces as well. And we will look upon the stability of submerged bodies and partially submerged bodies or floating bodies. And finally, we'll discuss about the rigid body motion part briefly. So let's see if we are able to solve some relevant problems on all the topics. I'm not sure whether we'll be able to cover all the topics, like problems related to all the topics thoroughly. So I suggest you might follow some textbooks to refer to those kind of problems. But still, let us try to at least look into the basic concepts or revise it once. And as per and similar to all the previous sessions, I will not dive deep into each and every topic very thoroughly that were discussed by Professor Chakraborty in the lectures. So my main goal would be to briefly go through the concepts and try to give you some relevant examples that will help you to solve the problems that will be asked today in the class, and of course in your assignments and your upcoming exams. Okay, so that would be the basic content of today's discussion. So I think with that we can start our discussion. Okay, so as I already mentioned, we will discuss about the hydrostatic forces on flat surfaces and curved surfaces. Starting with the flat surface, first of all we look into the governing equation or formula, as I must say, that helps us to determine the determine the uh, forces that act on a flat surface or a flat plate submerged in a liquid. Okay, of course within a certain depth. So the governing equation is given by this red box, which is yp is equal to yc plus ic by ayc. And just to show here, yp here is the center of pressure. We will come to what center of pressure really means. And yc here is the centroid of the object. Ic is the moment of inertia with respect to the relevant axis of rotation. With respect to the particular problem, we will see like which should be the axis of rotation to consider the moment of inertia, or evaluate the moment of inertia with respect to which axis. So that's this. A is the area of the submerged body, and yc is again is the centroid of the object. Okay, so the center of pressure, that is denoted by yp, is the pressure through which the resultant pressure force acts on the body. Okay, so there is the net buoyant force, say Fb, and the net pressure force, say Fp. So the buoyant force always acts through the centroid of the object, but the pressure force, because of the fluid, acts through the center of pressure given by Yp. Okay, the details of derivation I will skip for the sake of saving time. So for that I will suggest that you go back to the lectures. Maybe that would be a great source to look into, but eventually we'll see that this is the formula that we'll end up to, and for the majority of the problems that we solve, we will stick to this simple problem. But you will also, for the sake of better understanding, you will see that we will solve one problem today that goes back to the very derivation or the very source of derivation where we obtain this problem. Okay, so there is something known as the Verringon's, if I'm not wrong with the pronunciation, this Verringon's theorem. Okay, so that you need to look into it. If you look into lectures that were discussed by Professor Chakraborty, you need to maybe look into that Verringon's formula, and then you will be able to understand how this equation is derived. Okay, so I hope I am clear with that. So just I will kindly request you to just go through it. Yeah, Verrignon's theorem. Okay, just look into Verrignon's theorem. You will understand how this is obtained. And as you can see, since all these terms here in this right hand side of the equation are positive, so you will get a basic idea that this yp is always greater than yc. That is, the center of pressure always lies below the center of gravity of the object. Okay, or centroid of the object. Okay, so that's a fundamental understanding that you should know. And you will see that the first basic question that anyone would ask is why the center of pressure lies below the center of gravity, okay, or the centroid. So this again stems from the pressure distribution. So I've given a schematic diagram for understanding. Like if there would have been a scenario where the pressure distribution across the depth of a fluid varies such as this, that is a uniform pressure distribution, then you could have expected that the center of gravity or the centroid would coincide with the center of pressure. Okay, there will be no difference in the center of gravity or the center of pressure. But since we know that from the hydrostatic law, if you remember, that dp by dz is equal to rho g, or the pressure variation varies along the depth or varies along with the height across the depth of the fluid. So we'll see that the pressure actually increases as the depth increases. Okay, Thus the pressure here at this point would be higher than the pressure at this point, okay, because of the fluid. Okay, that's why to and you can see that if you take a mean of distribution of this force, you'll see that mean point of this force would be somewhere around here, like below the centroid of the object. Okay, so that is the basic logic why the center pressure usually lies below the centroid of the object. Okay, so with that, let us proceed further. So I think, and that's quite well understood, I don't think I need to dwell much upon it. But and for example, this again a very simple example that was taken in the class already. That consider a rectangular plate that is been submerged in the fluid, where the height of the plate is say h and the width is say b. Let me just denote it. Say the width, oh, it's already denoted, okay, b. Then, and say that the upper half of the upper edge of the plate is at a depth of say a from the free surface, and from that you can easily say that the net force that acts on the plate is given by net pressure force that acts on the plate is given by rho g AHC. Okay, and again, since this is a simple geometry, this can be easily evaluated. Okay, then A would be B times H, and HC is the distance of the centroid or the center of gravity from the free surface. So that would be A, that is this length, and H by 2, right? So since H by 2 is the center of gravity of this particular plate, and this centroid is a distance of H by 2 plus A from the free surface, so that would be your distance of the centroid from the free surface. And this, to find the and this actually gives you the net force, okay, the net force that acts on the body, but you need to find the point at which this force acts. Okay, so that's also very important to know. And this total force will actually not act through the centroid of the object, but rather act through the center of pressure. To find that, you need to take the help of this equation, that is yp is equal to yc plus ic by ayc. And here since the pressure variation is along this vertical height h, so we take this moment of inertia across this axis. Okay, across this axis. So if there will be a scenario where the pressure variation is along this, okay, then you should have taken the moment of inertia with respect to this axis. Okay, so this is how you choose with respect to which axis you take the moment of inertia. Okay, so from here you see, since the pressure variation is along this axis, so you take the other axis, you take the pressure variation of the other axis. So from that you get IC is BH cube by 12, area moment of inertia for a rectangular plate. A is again BH, and YC is A plus B by 2. Sorry, A plus H by 2. Okay, I'm sorry, it's H by 2. Yeah, to correct it. H by 2. Okay, so this is how you find the center of pressure, and the net force will act through this point. Now you may ask why you are finding center of pressure. So you will see that there will be some problems where you need to find the net moment that acts on this plate. For example, like the questions may be of this kind, like for example, this plate might be hinged at the bottom, and and the question might be something like, find the net force that may have to be acted upon this upper edge to stop this particular plate from rotating. Okay, basically it's a problem of a gate in the dams, where you need to find the net amount of force that has to be acted upon this edge, so that the gate does not open because of the net hydrostatic forces from the water that has been stored in the reservoir. Okay, so this is the basic motivation for understanding this kind of problems. Okay, and we will solve one such problem in today's example as well, that is already taken in the class, and some questions also we will discuss. Okay, so let us take one example now. Okay, hope the diagram is visible, and yeah, let us briefly go through it. Okay, so this is again a similar example that I already discussed now. That, for example, this is your plate that is being hinged at the bottom of the surface at here, for example, and the fluid is kept up to this height, say capital H. Okay, the basic problem is you need to find the net force F that has to be exerted at this edge of the red plate that has been shown here, so that the gate does not open. Okay, so that this gate does not open. So you can easily understood by now that these hydrostatic forces will tend to open this gate in this direction. Okay, so in order to prevent this gate from opening, you need to exert some force, say F, so that these forces are balanced. Okay, so you need to find that particular force F. And the type of questions that might, the way by which these questions might be varied in your exams would be, they might change the shape of this plate. Okay, of course it's very unnatural to have this semicircular plate, semicircular shaped gate, of course, but usually it is of course rectangular to, like, of course for the ease of construction as and also the simplicity of the force evaluation. But just to make these questions tricky, the examiners or the teachers might change the shape of the gate so that they can just test your knowledge. Okay, and for example, in this case it's a semicircular disc. Again, it's a bit more complicated than a rectangular disc, so we need to again treat it accordingly. Okay, we need to treat the problem accordingly. Okay, so let us look into it. Again, I think this was already taken in the lecture, but I will go through this example. Yes, I will go through the example once, because it will give you a very strong foundation for one of the problem that we will discuss today. That will be a very extensive problem. Okay, so in order to do that, let us just go through it once, and then maybe I will ask you to solve the other question, and when we discuss some problems. Okay, so let us go through it. So I think the geometry is quite clear, that this is the height of the liquid from the datum or the base is at H, height of the free surface, I must say. The say the center of pressure is at a depth of yp from the free surface. Okay, and let the height of this rotating gate, okay, be r. Okay, basically since this is a semicircular disc, I will just treat the radius of the semicircular disc as the height of this rotating gate. Okay, and this would be the basic free body diagram of the gate, that Fp is the pressure force that acts across along the center of pressure of the gate. F is the force that you need to determine, that is the force required to stop the gate from opening. And the other forces that will act is the reaction forces at the hinge, say OX and OY, where OY would be balanced by your the mass of the gate. Okay, so considering that the net moment across point O is 0, then we will have that F times R, or capital F times R, would be equal to Fp times Y1. Okay, where Y1 is the distance of the center of pressure from the hinge. Okay, which you can see, which it will simply be H minus Yp, right? Okay. And we know that Yp is equal to Yc plus Ic by Ayc. Okay, so now we need to find all this Fp and expression of Fp, and then you can find the value of F. Okay, let us see how Fp can be obtained. Okay, so in the case of a semicircular disc, okay, again this diagram does not look semicircular, I'm sorry for that, it looks more like an ellipse, I'm extremely sorry for that, but actually it is semicircle. Okay, and we know that for a semicircle, the centroid actually lies at a distance of 4r by 3 pi from the center, okay, or from the base. Okay, from the base, the distance of the centroid of the semicircle would be at the distance of 4r by 3 pi. Okay, so that's what is denoted here. Okay, so yc would be the distance of yc, okay, not yp. Yc would be the distance of h minus 4r by 3 pi. Okay, from the free surface, your yc would be at a distance of h, that is the depth of the fluid, minus 4r by 3 pi. Okay, this distance. So this will give you yc. Okay, I'm sorry that it's shown here, but since it's an extensive labeling, so you might miss out something somewhere. So if that's the case, you might ask me, but of course I will share the notes so you can refer to it. But if there's any doubt during the discussion as well, you can ask me. There is no problem with that. Okay, so as I told, since it's a semicircular shaped gate, so it's a bit tricky to find the net force that acts on the gate. So rather than directly implementing the formula of say rho g ah, so we would rather have to take the help of some integration so that we can find the net force, the total force that acts on the surface of this semicircular shaped disc. Okay, so yeah, so let us proceed further. So you will see that, let us first try to find the net force that acts on a particular area element at the disc. Okay, so consider that this is the, I think this would be better, I can zoom it. So this is your small elemental area of the semicircular disc. Okay, so this area can be found out by finding the distance, say these two lengths. Okay, so this would basically be, if this angle is d theta, say, then your, and say this element is a distance of r from the origin. Okay, origin or the hinge, I must say clearly. Okay, so this length would basically be r times d theta. Okay, this would be r d theta, and say this length is dr. Okay, so approximately, if this area is very very small, then you can find the area to be something like length into breadth. Okay, of course these are curved surfaces, you might question that, but for very very small elemental area, you can approximate these lengths to be of length, these curves to be straight lines. Okay, it's a very very good approximation for very small distances, like curves to behave as straight lines at very very small distances. Okay, so with that approximation, what we will consider that the area of this curved surface can basically be evaluated as length times breadth. So this length is dr, as is shown here. Okay, this is dr and this is r d theta. So the elemental area would be r dr d theta. Okay, so that's how we find the elemental area. Okay, sounds good. So let us proceed. I think I can zoom out a bit now. So dA is the elemental area, so it is r dr d theta. Okay, and for this elemental area, for this elemental area, if this is a distance of say r from the origin, okay, I will, for this particular problem, I will say origin and hinge, I will use origin and hinge, the hinge point interchangeably, so please don't get confused. Okay, so if this is r, okay, the vertical height of this particular area from the base would be r sin theta, correct? So from the free surface, okay, from the free surface, the distance of this particular elemental area, or the centroid of this particular elemental area, would be the distance of h minus r sin theta, correct? So that's why this distance is h minus r sin theta. Okay, so the elemental force, say F, that acts on this particular elemental area would simply be rho g times dA times, rho g dA times the height, correct? Right, the height or depth at which this elemental area is located. Okay, so that's the basic logic that we'll use. So from that, you can, if I go back here, you'll see that the net elemental force that acts on this particular elemental area would be rho g times the elemental area r dr d theta times the depth of this particular area, okay, h minus r sine theta. Okay, so I hope this is clear. And if you look back into this equation, so if you see that since we need to balance the net moment, this F times R, so what we will do is we can, since we already know that the elemental force, that is dF, we can find the elemental moment, say dH, it is noted here, of this particular area, and then we can conduct the integration over the given area of the semicircular plate, and then balance it with the product of F times R. Okay, so this, from this, if you divide it by R, you will easily get the value of F. So that's how we'll proceed. Okay, so let us do that. So if F is this, then dH would be dF R sine theta. Okay, now you might ask how it is there. So let me just go back. Okay, I'm going to and fro a lot, so please, I apologize for that. So if this is R, okay, and this is R sine theta, so if you remember, for evaluating the moments, we see that we multiply force times the perpendicular distance from the axis of rotation. Okay, so since the perpendicular distance of this particular area from this axis of rotation is r sine theta, so that's why we need to multiply it with r sine theta and not r. Okay, so we need to multiply it with the perpendicular distance. Okay, so we multiply with r sine theta, this times r sine theta. Okay, this will give you the elemental moment. Okay, so from that you can see that just multiply this with r, then if you simplify it a bit further, you will get dH, or the net elemental moment, as h r square sine theta minus r cube sine square theta times rho g d theta dr. Okay, so now you can see that to find the net moment, you need to do a double integration of over theta and r. Okay, so if you go back to the diagram, you can easily say that, if I go back here again, so you can see that since theta varies from here, the theta will vary from 0 to pi, okay, or 0 to 180, and r will vary from 0 to capital R. Okay, so those would be the limits of our integration. Okay, so if you do that, carry forward the integration, you will see that, let us first do the integration with respect to r. Okay, so this will become h r cube sine theta minus r to the 4 by 4 sine square theta by sine square theta can be replaced by 1 minus cos 2 theta for integration. You can integrate it easily. Then we integrate respect to theta. Okay, so h r cube by 3 would integration of sine theta would be minus cos theta, limits from 0 to pi, then minus r to the 4 by 8, 2 will go here, so we will have integration of 1 minus cos theta would be, with respect to theta, would be theta minus sine 2 theta by 2. Okay, because integration of cos theta is cos 2 theta would be sine 2 theta by 2. So now if you put the limits of integration, you can easily see that the total moment with respect to the origin O would be given by, and this of course is equal to F times R, if you remember, so it will be rho g, Fr would be equal to rho g 2h r cube by 3 minus pi r to the 4 by 8. Okay, and if you just divide it by r to get the net force, it would be rho g times 2h r square by 3 minus pi r cube by 8. Okay, so this will give you the net force that is required to prevent the plate from the plate or the gate from opening. Okay, so this is the example that I wanted to discuss. Okay, so I hope this is clear. Okay, So is this part clear? This discussion clear? We'll move on to the next topic. Okay, I'll wait for say 1 minute. Okay, okay, okay. Then okay, if it's clear, then we can proceed further. Okay. So the second topic or second important topic. I'm sorry that we wanted to cover is the force on the curved surfaces. Okay, so again we'll use a similar idea that a surface that is submerged in a liquid will have net forces acting upon it. Okay, so that's the basic principle, and for all these cases, just to reiterate, we are still under the umbrella of fluid statics. So we are, for all these cases, the fluid is at stationary state. Okay, so that's why only normal force components exist. So if you remember the Mohr circle that we discussed, Professor Chakraborty, the Mohr circle of this particular uh, case was or boiled down to only a single point in the Mohr circle. Okay, so Mohr circle, if you see, is basically a way or method to represent the net stress that acts on a surface or on a object, where you represent the net normal forces and the shear forces. And since there was no shear forces, primarily because the fluid is not at motion, that's why only normal forces exist, and it boils down to a single point in the Mohr circle. Okay, so that's what also discussed in the lecture. So if you want, you can just go back and look into it. Also, where we can easily now correlate how the static nature of the fluid affects the stress distribution in the flow field. Okay, so let us proceed. So again, similar idea. So now, instead of dealing with a straight surface or flat surface, we will deal with a curved surface. So again, this is in a way, if you see, it might be complicated for complex geometries, but for the scope of this course and for the scope of most of the basic fluid mechanics courses, okay, or standard fluid mechanics courses, not the advanced or the specialized topics, we usually deal with simple curved surfaces, okay, very simple geometries, so that the analysis becomes a bit more simpler. Okay, we will not deal with very complex geometries, and I personally didn't look into it, so I will not be able to answer it, the implications of curved geometries, but sorry, complex geometries, and how it and the force varies. But for simple geometries and for most of the standard fluid mechanics courses, this idea will suffice. Okay, so with that, let us proceed. So consider that this is a curved surface that is being submerged in a fluid. Okay, and again, this is the free surface. This is the curved surface submerged in the fluid. So what we need to do is, basically, now, since it's a curved surface, you can understand that the net force can be easily dissociated into two components, the vertical and the horizontal component. Okay, so we'll do the same. We'll try to dissociate the force from the fluid on the curved surface as vertical and horizontal components, and let's see what happens. So if you look into the horizontal components, or the forces along the x direction, you'll see that the net force along the horizontal direction would be, here is the force Fh1, okay, and here would be the force Fh2. Okay, so, and say the net force along the positive x direction is say Fh, then if you just consider the fluid to be in equilibrium, then you will have Fh plus Fh1 minus Fh2 is equal to 0, or Fh to be equal to minus Fh1 minus Fh2, okay, or Fh2 minus Fh1, okay, the net force along the horizontal direction. Okay, and if you remember, the net force that acts on this horizontal surfaces is actually the force that acts on the projection of this particular curved surface. Okay, so if you remember, this the projection of this particular curved surface would actually be a rectangular plate. Okay, so to evaluate the horizontal components, we basically just find the net force that acts on the projection of these curved surfaces. Okay, that's why it is simple. Now if the surfaces are complex, then the analysis becomes a bit more difficult. Okay, so that we'll not deal with in this course. So that's why for these simple curved surfaces, the projection of this curved surface will simply be a rectangular plate. For example, if this is a curved surface, then the projection will be something of this kind, right? And we need to find the net force that acts on this particular projection of the curved surface. And the vertical component is much more simpler. Is basically the net force that acts along the vertical direction is balanced by the weight of the fluid engulfed by the curved surface. Okay, so whatever is the fluid that is engulfed within this curved surface is balanced by the vertical force Fb. Okay, so in order to understand that, let us consider an example, a very simple example that actually helps us to understand the curved surface forces logic in a very what to say, satisfying manner. Okay, so consider that this is a scenario. A cylindrical shaped tank, for example, is being placed in a fluid where one of the surface where the level of fluid at one of the surfaces is given by this. Okay, and at the other side the level of fluid is given by this. Okay, so the depth at which the fluids are located are at or height at which or depth at which the tank has been submerged is different at both the sides. Okay, of course it's a very no, actually it can occur. If you design accordingly, it can occur, but it may seem a bit counterintuitive at the beginning. Okay, but depending upon the scenario, it may occur. Okay, and say that this surface has fluid within, like the half of the cylindrical shaped surface has fluid engulfed within this region. Okay, so as shown here. So this region has fluid inside it, and for other side this part is hollow, but the other half, other sector, is engulfed with fluid. Okay, it's filled with fluid. So the question is, or it's actually not the question, it's an example. So the task is to find the net vertical and horizontal forces that acts on this particular cylinder. Okay, so to find the vertical forces, it's very simple. Again, as I mentioned, just to find the net weight of the fluid that is engulfed in this region. Okay, so let us dissociate it into two parts. So first is this half of the cylinder. Okay, so we will just do volume times the density. So of course m times the acceleration due to gravity. So volume of the fluid that is contained within this half of the cylinder would be pi r square L by 2. Okay, simple enough, right? If the volume of the entire cylinder is pi r square L, then for this half cylinder it would be pi r square L by 2. Okay, L is the length of the cylinder. For the second part, this is 1/4 of the cylinder is contains the fluid, so it would be pi r square L by 4. Okay, so this would be total volume of the fluid inside the cylinder times rho F times G. Okay, so this would be the net vertical force that acts on the cylinder because of the fluid. And for the horizontal components, it's again similar idea. So rather than dealing with this curved surface, we will rather deal with the projection of this curved surface to find the net horizontal forces. Okay, so for this half of the cylinder, okay, say this is FH1 and this is FH2, then FH1 would be again we use the same formula. F is equal to rho g h times A. Okay, so H and A would vary depending upon the the volume of fluid that is contained in the cylinder, and H will vary upon the free surface. Okay, so rho g is same, rho fg is same as it's shown here. The projected now the area is actually the projected area of this particular cylinder. So the projected area of this particular cylinder will be the rectangle of dimensions 2r times the length of the cylinder, right? So 2r times L, and the h, if you remember, is the distance of the centroid from the free surface. So the centroid, it would be a distance of r from the free surface, if you remember. So it is r. Okay. Similarly, for the second part, fh2 would be similar. So now rho fg would be same, but a would actually be the projection of this part of the cylinder, this half cylinder, okay, or 1/4. So it would be now r times L. Okay, the projected area would be r times L. Okay, and since the free surface is at this location, okay, it's different from the other side, so the distance of the centroid would basically be not of the curved surface, okay, the center not of the curved surface but of the projected area. The distance of the centroid of the projected area from the free surface would basically be r by 2. Okay, see, if it's a rectangular shaped plate, the projected area, so centroid would basically be half of the, say, this height. Okay, so it is r by 2. Okay. And if you remember, just again one more subtle point. Okay, I hope this part is clear. Okay, just to know the evaluation of the force on the curved surfaces, this part is clear. Okay, so okay, you can just tell if there's any doubt. But the other thing is, if you remember, there was one point that was discussed by Professor Chakraborty in the class, that again it's a very subtle point, and there are some examples in some textbooks if you want to look into it. So that if there are some scenarios where rather than the curved surface holding the fluid, if it's the other way around, okay, for example, if it would have been a scenario where this part is hollow, okay, okay, consider a scenario where say this part, we just neglect this part, okay, just neglect this part for now, okay. I think I should just draw it. So for example, this is your curved surface, say, half part of the cylinder, and this is your free surface. Okay. So now you can see that rather than the fluid, the surface containing or holding fluid, it's rather a hollow surface, a hollow concave shaped surface that is holding the fluid from the, like, it's not holding but stopping the fluid from the other side. Okay, so you see that there is no fluid here, it's not holding any fluid, but rather acting as a gate or a dam to hold the fluid in this part. Okay, or to hold the fluid in this region. Okay, consider it basically a reservoir of this particular shape, semicircle shape, okay, or a concave shaped surface. Okay, and if you remember, for this kind of scenarios as well, Professor Chakraborty pointed out that you can consider the same evaluation, okay, same evaluation technique, that just assume that for these surfaces, for this kind of surfaces, just assume that this part of the cylinder holds holds fluid which is in this shape. Okay, and then with this assumption, carry forward your calculations. Okay, so you will see that you will again find the same way, that if you consider, we use different color. Okay, so assume that this is the amount of fluid that is being held in this hollow cylinder. Okay, I'll do something like this. Okay, it's a hollow space. Okay, so evaluation for the net force that acts on this curve surface will be exactly the same. So Fv would be pi r square L by 2 times rho Fg. Okay, and Fh projected area is 2r times L, density is rho F, then G times this depth of the centroid of this projected area would be R. Okay, so same technique to evaluate the net forces. Okay, so rather than being complicating it, just assume that it holds fluid in that particular region and then evaluate the vertical and horizontal components. Okay, so that's how you do it. That's how it is told. Again, the details for now I am not able to resolve, but this is how you handle this kind of problems. Okay, so one of the examples I think you will see in today's problem solving part, that it will have this kind of surface, then you need to use that same logic. Okay, that's why I just emphasized it on a bit. Okay, so for example, and just another example here. Okay, let us proceed. That rather than having a defined curved surface, for example a semicircle or or even as say other some definite shapes. Okay, you might have curved surfaces. You might have curved surfaces that may be defined by using some equations. Okay, by some relations. Okay, for example, if this is a curved surface, that is, I'm sorry, if this is a curved surface where the relation is, or the curved surface is defined by x is equal to ay cube. Okay, it may be like you may have something like x is equal to 4y square also. Okay, a simple parabola. This is a cubic curve. Okay, but you might deal with parabola as well. Okay, but depending upon the given problem, you might have to handle it accordingly. Okay, so in this kind of problems, you need to just it will be a bit more complicated, a bit more detailed analysis, but logic will remain the same. Okay, so consider that this is the curved surface and fluid is kept up to height of this is kept up to this particular height. Okay, then similar to the previous example of the semicircular shaped gate, we need to again take the aid of calculus to find the net force that acts on this particular area. Okay, since there is no definitive way to evaluate the net force using some simple relations, we need to take the help of integrations to find the net force. Okay, so let us consider elemental area of length dl, say, as it is shown here. Okay, and if this is and if this point is at an angle of say theta from the vertical. Okay, if you just zoom it in, okay, and just draw it here again, you'll see that this angle that it makes would also be equal to theta. Okay, so the details is shown here how it will be theta. Okay, you can just look into it. Then if this is dl, then say this is dx and dy, and you say that dx would be dl cos theta and dy would be dl sin theta. Okay, and dl will basically be the square root of dx square by dy square. Okay, plus dy square. Very simple. Then the net force, the net vertical force that acts on this particular of this particular area would be, or elemental area would be, pressure times the length times w. Okay, pressure would be rho g d minus y. Let us see why it is d minus y, and the area, that is dl times w. W is your width. Okay, say if this is the height of the free surface from the reference heights, say this one datum. Okay, and say if this elemental area is located at a distance of y from the reference datum, or datum I must say, that's the correct terminology, then the depth of this particular elemental area from the free surface would be at a distance of d minus y. That's why we use d minus y. Okay, so to find the net horizontal components, okay, so this is the dissociation. So if this is the net sorry, just wait for a minute. Yeah. So this is a net force that acts on this particular elemental area, then we can dissociate of the or net force that acts on this particular curved surface, then again you can dissociate it into the vertical component and the horizontal component. So from this dissociation you can see that if this angle theta, then the net vertical component is Fv is F cos theta and Fh is F sin theta. Okay, so since we're dealing with the elemental areas, we again need to dissociate into the elemental force components. So we'll have dFh as PWdL, where WdL is the elemental area, okay, P is the pressure, PWdL sin theta, since we are dealing with the horizontal components, you can see how we got sin theta here, okay, and since dl sin theta, if you remember, is dy, then dfh would be pw dy, okay. Now pw is rho g d minus y, so we can get dfh as rho g d minus y w dy, and if you need to find net force, just integrate it from 0 to d, okay, because this is the height or distance up to which your area varies. So net horizontal force component can be found out like this. Similarly, for the net vertical force, same logic, df would be pw dl cos theta, dl cos theta is dx, if you remember. So we'll have rho g d minus y w dx, okay. So now you might ask, see, we have the limit of integration from, we know where y varies from 0 to y, okay, but we do not know how x varies, okay. Of course you can find from the relation, but not to complicate it, but you know that how y varies, okay. So to do that, you just need to do a simple change of variable. So either you can keep dx as such and represent y in terms of x, or much more simpler would be keep y as such and replace dx, because you already know the limits of integration for y. So dx, you know, x is equal to ay cube. If you see here, x is ay cube, then dx would be 3ay squared dy, okay. Then just replace this one in this equation, you will get fv as integration from 0 to y equal to 0 to y equal to d rho gd minus yw 3ay squared dy, and from this you can easily find the vertical component as well. So the net resultant force would basically be F is equal to square root of Fh squared plus Fv squared, okay. So it's not that complicated, but in exams also you might expect similar type of scenarios where you will be given the equation of the curved surface and you may need to find the solution, okay. So I will just give you an idea that it's sometimes difficult to remember the formulas, so maybe just have a practice of doing such force decomposition and finding the elemental areas, and then getting formed the integration, okay. That would be a better way. And not only like for objective type of exams, I think it's difficult to emphasize upon the utility, like knowing the formula is of course most of the times usually more than enough, but for example, if you are dealing with your exams in your, say, institute, in your colleges or universities, where you may deal with subjective type of questions, okay. So, and where if you don't remember the formula as such, you can go ahead and start with from scratch, try to show the force decompositions and integral calculus parts, and even if you are not able to reach the final answer, or your final answer is incorrect by some, if it's a bit incorrect, then also if you show these kind of calculations, the evaluators or the examiners will understand that you know the concepts properly, and they will give you or evaluate you accordingly, okay. So that's a very a benefit of trying to solve problem from scratch, okay. So, and I think that in the in the run of being in the run of trying to solve problems quickly and just depending on formulas solely, we sometimes, I think, ignore the importance of these derivations, okay. So I think, and as you proceed further in your academic career, okay, you'll see that these are the these are the basic principles are the ones that are more appreciated, okay. So rather than knowing the formula, examiners, evaluators, or anyone who will evaluate your work will appreciate you if you are able to show the basic the problem from the perspective of basic principles, okay. Sorry I took so much time in this discussion, but just wanted to know let you know about the importance, okay. So if there's any problem, if there's any doubt in this particular derivation, you might ask, or else I will proceed further, okay. So two topics remain: stability of floating and submerged bodies, and rigid body analysis, okay, rigid body motion analysis. So I'll quickly go through both of them. For the stability analysis, I won't go into the derivation, it's a very extensive derivation, and so to save time, I will just discuss the final formula again. Sorry for that, but for the better understanding and understanding derivation, I think you should go back to the lectures, and I emphasize that you go back to the lectures so that you understand how the formula was derived, okay. That's the first point. And second, again, we'll briefly touch to the topic or example that was taken by Professor Chakraborty for rigid body motion, okay. And then I think it will take say 10 more minutes, 10 or 15 minutes, I think. I'll try to go fast, and then we'll discuss some problems, okay. So yeah, that's what I want to discuss. Let us now start, okay. So for submerged bodies, that is bodies that are completely submerged under fluid, okay. So let's consider a body of this example, okay. I'm sorry, let us consider an example of body of this particular shape, okay, where the upper body is designed, the body is designed as such that the the center of buoyancy would be above the center of gravity, okay. So that's how this body is designed. Like, you may assume a body of such shape that the lower part, even though the area is small, but the mass or the weight is higher, so the center of gravity is aligned towards the lower part of this particular shape, okay. But since the upper part, like this upper part has a larger area, and of course is the weight of this upper part is lower than the weight of this lower part, then or in specific terms, the density of this upper part is lower than the density of this particular region, okay. Then you might assume that since the area is higher, and you can see that since the buoyant force depends on, if you remember, F is rho g a h, right, and since it depends on area, the higher the area, larger will be the buoyant force, okay. So that's how we consider the shape of this body, so that the demarcation between the points of acting of the buoyant force and the gravitational force is easily observed, okay. Since the body has higher weight towards the lower end, the center of gravity would be shifted towards the lower end, and since the body has a larger area at the upper part, the center of buoyancy will shift at the upper part, okay. So that's how the body has been designed, okay. So let's look into it now. Consider that we displace this, we give a slight perturbation or slight displacement to this particular body, okay. Like, we give a certain amount of force to this particular body at this point, okay. Say this is basically a displacing moment, okay. So what would happen is that since the body has shifted, okay, the element of the body has shifted, so if you remember, your center of buoyancy was above the center of gravity, okay. So since the body has been shifted, okay, so now you can see that the center of buoyancy is here and the center of gravity is at this point, okay. So the gravity will the net gravitational force will act along through the point G in downward direction, and the net buoyant force will act through point B in the upward direction. Okay, so you can see that the displacing moment is along the, say, the clockwise direction, but the force or the orientation of force along the center of gravity G and the center of buoyancy B is such that it is giving a restoring moment or a net moment in the direction opposite to this displacing moment, which is encouraging this body to go back to its original position. Okay, that's why if there's a scenario where your center of gravity is below the center of buoyancy, or the center of buoyancy is above the center of gravity, we see that this kind of equilibrium is also known as stable equilibrium. Okay, that if you give certain displacement to the body, then it will try to generate a restoring couple as such that it tends to get back to its initial position. Okay, of course, if the displacing moment is very very large, then the body might go might fall down or even undergo rotation. If it is submerged in the fluid, then it might undergo rotation. Okay, but if the displacing moment is small enough or considerably small enough, then it will tend to go back to its initial position. Okay, and if there's a scenario where your center of buoyancy and the center of gravity coincide with each other, then it's basically a neutral equilibrium. Okay, so if you displace the body, it will tend to remain at that particular alignment. Okay, to be like, if you give it displacement, then it will tend to remain at that shape. We tend to remain with that at that particular particular configuration. Yeah, that's the correct word for it. But if the scenario changes, okay, for this particular, if the scenario changes where your center of gravity is above your center of buoyancy for submerged bodies, okay, then you will see that the direction of the restoring couple is actually, or restoring moment is actually, aids the displacing moment, and thus it will tend to generate an unstable equilibrium. Okay, so I don't know if I could show it here or not, but maybe I can leave it to you as an exercise to show how the configuration where the center of gravity is above the center of buoyancy generates an unstable equilibrium for submerged bodies. Okay, so this is something that you can look into it. Basically, you will see that if center of gravity is above the center of buoyancy, then gravity will act along this direction, buoyancy will act along that direction. Then you see that this couple actually aids your displacing moment, so body will again try to displace further from its initial position. Okay, so that's what unstable equilibrium basically means. But you can maybe look into maybe redraw the diagram that makes sense. Like, you can maybe display invert diagram, like maybe you draw something like this, right? G would be at the upper, would be above, and buoyancy force, the center of buoyancy would be below. Then you can draw a diagram and show the unstable equilibrium condition. So the important part, or the interesting configuration, is examples are for the stability of floating bodies. Okay, so in the exam or in the questions, in the assignments, I've not seen the assignments, so I don't know, but in the assignments there might be questions where you might be asked the stability of floating bodies. Okay, so for submerged bodies, I don't think there will be any question. It's just for a better understanding and introduction to stability. So I don't think there will be any relevant questions from submerged bodies part, but from floating bodies there might be some questions. Okay, so let us now quickly look into it. Okay. So again, just to reiterate, for this case also, for floating bodies example as well, we are again considering bodies which are symmetric about one of its axis. Okay, basically in this case would be along this axis perpendicular to this page. Okay, so we'll consider the stability of bodies, they are symmetric in nature. Okay, for again asymmetric bodies, the analysis would be different, and which is again beyond the scope of this course and or any basic fluid mechanics course. So we'll not look into it. So the limitation of our analysis again is limited to symmetric bodies along this particular axis. Okay, so that's what you need to remember. So with that, let us proceed. I know this was already taken in the class, but just for a revision, let us just quickly look into it. Okay, so for consider the body of this shape. Okay, where half of its body is submerged in the liquid and some portion is floating above the free surface. So basically, it's a partially submerged or floating body. Okay, and this again, if you see, is a very good example or approximation of ships. Okay, of course, for ship, the floating part would be much larger than the submerged part, or like at least much larger than the part that we have shown here. Okay, but this is how we just, it's a like that's the motivation behind understanding the stability of these floating bodies. Okay, so with that, let us proceed. Let the edges this and this point be A and B, and in this case you will see that the center of gravity say is G and the center of buoyancy is say B. Okay, now consider that if you give a slight and now you can understand why this is the case, because if say there is no specific shape to a particular body, like we are not, what to say, designing it in a way that generates that shifts the center of buoyancy above the center of gravity, like if there is no, what to say, additional change that is being made in the this particular body, so that the positions of center of gravity and the center of buoyancy is deliberately changed. So you can, if you remember, naturally, if this is the case for submerged bodies, if you remember from our first example we discussed, the center of buoyancy like depends on the area which is being submerged in the body, which is being submerged in the fluid. Okay, so the is a significant area or significant area of the body is being submerged in the fluid, then the center of buoyancy will naturally lie below the center of gravity. Okay, that's what I wanted to discuss. And another important fact is that the position of the center of buoyancy changes depending upon the area that is being submerged in the fluid. For example, if the area, this is the particular area that is now being submerged in the fluid. Okay, but now if the configuration of this area that is being submerged in the fluid changes, then the center of buoyancy will also shift. Okay, that is what is the basic concept that you need to remember for understanding the stability. Okay, so we'll do the same thing as I shown here. We will now give a slight displacing moment or displacing force, say across this edge. Okay, so what would happen if we apply some force here? This part, this edge B will go down. Okay, will go down, and this A will go up. Okay, so B will now hold a position of say B dash, and A will be at A dash. Okay, center of gravity will stay wherever it is. It will stay at its own location, say G, but what would change is the center of buoyancy. As I told you, the center of buoyancy depends upon the configuration of the area that is being submerged. Okay, and since the configuration of area that is being submerged has been changed because of the application of this force, the center of buoyancy is now shifted from B to B dash. Okay, I should give it say B dash. Okay, so now you can see that since there is a slight distance between the points of application of the center, the weight of the object to the center of gravity and the buoyant force Fb, you will see again that there is a generation of a restoring couple. Okay, restoring force that acts along the counterclockwise direction, and this is the restoring couple that would again return the object to its original position, okay, or basically make this configuration stable, okay. And you'll see that if I go back here now, if you extend, like if this is the shift, the new center of buoyancy, and if you now extend this a line from the center of buoyancy to a distance in a way that this line intersects the central axis at which your center of gravity lies, then the point of intersection, distance between the point of intersection and the center of gravity g will give you the metacentric height, okay. This point where the intersection occurs is known as metacenter m, and this distance between m and g is known as the metacentric height, okay. So this metacentric height is actually your important, or one of the the important parameter for understanding the stability of floating body. So if this metacentric height is large enough, the body is much more stable, okay. So again, there is a detailed derivation for finding the metacentric height for this type of symmetric bodies, okay. So where if I look into this diagram, okay, so from here you can find gm, okay, to be equal to cbm minus cbg, where cbm minus cbg, okay, it is equal to Iyy by the submerged volume V minus cbg, okay. So cbm is given by Iyy by V, where V is your submerged volume, okay. Again, the limitations is that theta, the displacement, is small, okay, and z is the axis of symmetry of the body, okay. Z is this axis, okay. Z is the center of symmetry of the body, okay. As I already mentioned, this analysis is limited to your symmetric bodies. That's why we cannot extend this analysis to complex shaped bodies or asymmetric bodies, okay. That's the limitation of our study, but you need that, but it is sufficient enough for this particular basic fluid mechanics course, okay. So the stability criteria for this submerged bodies again given by the metacentric height. So if m is above g, that is your metacenter is above the center of gravity, then the body is stable. If there is a scenario where the metacenter is below the center of gravity, then the configuration is unstable, and if metacenter and the center of gravity coincide with each other, we get a neutral equilibrium, okay. So that's basically the discussion on the stability of floating bodies. So I will quickly go through the last topic for today's discussion. It is the rigid body motion, okay. So let us just go through it quickly. Sorry for and then we'll take some examples, okay. So if you remember, in the last class also, we discussed about the governing equation for fluid statics. So there we saw that, so this was basically the governing equation for fluid statics. Now the basic question was, if the fluid is static, why there is an acceleration term, okay. So if you remember, I told that this acceleration term exists because there might be scenarios or conditions where the fluid might be at motion, but still the net shear forces would be zero, and if the shear forces are zero, then again these kind of configurations or scenarios also again fall under the umbrella of fluid statics. That's why, and these kind of scenarios where fluid might be at motion, but there are no relative motion between the fluid layers or no shear forces, these kind of scenarios are also known as fluid under rigid body motion, okay. So for that we'll consider one very simple example, where a tank, for example, a tank is moving over a surface and is undergoing some certain acceleration, okay. And because of this certain acceleration, the free surface or the shape of the free surface changes, okay. So it's understandable, like if this car or this tank is moving very, very fast, then the shape of the free surface might change accordingly and may obtain or may get this kind of particular shape, okay. So like may be changed into this particular shape. And now you can see that if this proceeds further, now you can see that if it goes up to an extent where the free surface obtains this kind of particular shape, then there is a chance that the fluid might spill out. Okay, so this is the particular problem that we will discuss. Again, there can be several examples, but for this particular case, I will just stick to the example that was taken in the class. We will look into the example of a tank moving on the acceleration and try to implement the concepts of rigid body motion and find the net height delta h, or the least value of height, say delta h, that is this height, change in the height delta h, that would prevent the any kind of spilling from the tank. Okay, so that's our motivation. Let us start. Okay, so for free surface, we see that the net change in the pressure would be equal to 0. Across the free surface, the pressure must be a constant. So, and since pressure can be considered, and for free surface is a surface, so it is a variable of two variables. It's a function of two variables. Okay, say x and y. Then we can write dp as dou p by dou x dx plus dou p by dou y dy. Okay, and I know that most of you will already know how this complete derivative dp is represented in terms of partial derivatives, but if there's any doubt, you can just like take this for like take it as it is. Like if say a function is a function f is a function of say x and y, okay, then the complete derivative of function f, that is df, can be represented as dou f by dou x times dx plus dou f by dou y dy. Okay, this is how you present the complete derivative in terms of your partial derivatives. Okay, and say if it's a function of dz, then again you can write say dou f by dou z dz. Okay, just extend it to say z as well, function of x y z. Then okay, so this is how you do it. And since dp is equal to 0, then it will imply that this is also equal to 0. Okay, so now what we need to do is we need to find the expression for dou p by dou x and dou p by dou y. Okay, so for that we will again take the help of the equations for rigid body motion. Okay, so we will have dou p by dou x minus dou p by dou x plus rho bx is equal to rho ax. Okay, because there is an acceleration along the x direction, so we will consider rho ax. Okay, so and since there is no body force along the x direction, so dx is equal to 0, so we will have dou p by dou x is equal to rho ax. Similarly, along the y direction, since there is no, for this particular case, since there is no acceleration along the y direction, so rho ay is 0, but dou p by dou is equal to rho plus rho by equal to 0, and by is minus g, considering direction of gravity along the negative z direction, so we will get minus dou p by dou is equal to rho g. So from these two equations, you can easily just replace dou p by dou x and dou p by dou y in this equation. Then you will get dou p by dou x is minus rho ax and dou p by dou y is minus rho g. From that you will get dy by dx is equal to ax by g. Okay, and dy by dx again can be considered as a slope of this particular free surface. Okay, then tan theta would be equal to ax by g, or if I go back here, okay, so if say just give me a second. Yeah, say that let us I didn't mark it, so say that this is the additional height that arises, this is delta h, and say this is L. Okay, and this is say theta. Okay, then delta h by L would be equal to tan theta, that would be equal to ax by g. Now our task was to find delta h, so delta h would be del ax by g times L. Okay, so if we see that h plus delta h, if we want to find delta h, if h naught plus delta h, where h naught is the initial height of the fluid, is less than the height of the tank, then the fluid will not spill out. Okay, but if delta h plus delta h is greater than h, then the water may spill out. Okay, so that was the example that was taken in the class to understand rigid body motion. So I will also stick with it. And for at least for today's case, I do not think there are questions that are related to rigid body motion. There might be questions in the next week's session, so we'll deal with that. But for now, I think it would be fine. So we can, end our end our discussion on the revision for the concept of previous week. And now I think we can directly start with the problem solving part. Okay, so let us look into. I hope this is clear till now. Okay, it's just a revision of whatever that was discussed. So okay, so if that's the case, then let us take some examples. Okay, so let us look into question number 1. Okay, I hope the screen is visible. Okay, so the question is, which of the following statements is or are incorrect? Okay, a hydrostatic force on a submerged horizontal flat plate at rest is the same as that of a flat submerged horizontal plate rotating uniformly around the vertical axis passing through its centroid. That's the first statement. Second is hydrostatic, I should not mark it, please. Horizontal flat plate rotating uniformly around the vertical axis. Okay, something like this. This will be the flat plate and this rotating around the vertical axis. Okay, this is what the question asks. Okay. Second option is hydrostatic force on a submerged horizontal flat plate at rest is pi times greater than that of a plate submerged at a horizontal flat plate rotating uniformly around the vertical axis passing through the centroid. Okay. C is hydrostatic force on the submerged flat plate is at rest is pi times less than that of a plate submerged horizontal flat plate rotating uniformly around the vertical axis passing through the centroid, or all of the above. Okay, so this is your first second configuration. This is your first configuration. Okay, and okay, this is rotating, say with a angular velocity of omega. Okay. So the question is, there are three statements. So first statement say that the hydrostatic force acting on this horizontal flat plate remains same whether or not this is rotating or being stationary. Second statement says that for this configuration, the stationary state, it will be pi times greater than the rotating one. Third case says that for a stationary case, the net hydrostatic force will be pi times less than the force acting on the rotating plate. And these all of the above. All of the options are incorrect. Okay, so you might choose the correct option. So I will give you say 2 minutes to look into try to solve it. Okay, then we can proceed. It's a conceptual question, I think, so there is no detailed derivation there. So yeah, maybe you can look into it. Okay, one more minute. Okay. So it was actually a tricky question. Tricky, or I must say, a question used to test the concept. So actually, at first glance, it seems a bit tricky. Like, of course, options B and C are diverting us from our understanding, but the correct answer would be that options A is correct. So question is which are incorrect. So option B and C are incorrect. Okay. Why, you might ask? So if you recall, okay, uh, the if this is horizontal flat plate, the net force, hydrostatic force, would be given by F is equal to rho g a h. Okay, since both of the plates are at the same depth, okay, and the area at which the hydrostatic force acts remains the same, irrespective of it being uh, stationary or rotating. That's why the net hydrostatic force remains the same. Okay, but again, I understand the confusion. So the confusion would be that we take a very important assumption that we will consider the scenario where the the rotation of the plate won't cause much what to say, change in the fluid motion. Okay, so since the fluid is at rest, so the rotation of plate won't cause any kind of motion to the fluid. So if that's the case, the fluid will still remain at rest. Okay, so that's the approximation that you need to consider while answering this question. So if that's the case, then since the hydrostatic force does not depend on whether the plate is rotating or not, the only limitation is that the fluid has to remain stationary. Okay, so in that case, and we're only asked the hydrostatic force, so it will mean that even after rotation, the hydrostatic force will persist, so the fluid is at stationary state. Okay, so since the area at which the force acts is not changing and the depth at which the plate is placed has not changed, that's why among both of these options, all these three options, option A is the correct one and B and C are incorrect. Okay, so of course, students, like, I think, might have some conflicting thoughts, or the participants here might have conflicting thoughts, but this is how the problem has to be approached for this particular case. But again, a counterintuitive argument can be made, and we will appreciate that. Okay, that why it might be different. Okay, so discussions are all welcome on it, and the basic, I would say the basic argument would be that the rotation, if we are not in if we are not considering the in-viscid assumption, then the rotation of plate via the no slip boundary condition might cause the fluid to also rotate. And if that's the scenario, then again the net forces or the hydrostatic force assumptions might change, and we might not be able to impose the net force analysis equations on this particular geometry, okay, or this particular configuration. So again, conflicting arguments might occur, but from a simple perspective, if you impose the in-viscid assumption, then the rotation of plate won't cause any kind of motion to the fluid. That's why it will remain same, the force will remain same. Okay, eh? Yes, option A is correct. Yeah, so this question again, like, I think was a good source of discussion, and of course discussion are always welcome. So even after today's class, if there's any doubt, you might put the discussion in the discussion forum, so either me or Prof Chakraborty himself might answer the questions. So all the discussions are always welcome. Okay, so that, but again, let us still proceed further. So question 2 is dams are built much thicker at the bottom part. Bottom part of dams are subject to large forces as the pressure forces increases with depth. Okay, these are two statements. So the options are, both statements are individually true. Statement 2 is the correct explanation of statement 1. Both statements are individually true, but statement 2 is not the correct explanation of statement 1. Statement 1 is true, statement 2 is false, statement 1 is false, statement 2 is true. Okay, so which is the correct option? Yeah, that's correct. Option A is correct, that dams are built much thicker at the bottom part, primarily because hydrostatic forces changes with depth, and the hydrostatic forces are larger as we go deeper in within the fluid. That's why the dam has to be built much more thicker to withstand those increased hydrostatic forces. Okay, that's why statement 2 is a correct explanation of statement 1, and both other statements are correct. Okay, this is the correct answer. Let us proceed further. So the question is, on a plane surface, the hydrostatic forces form a system of parallel forces, and we often need to determine the magnitude of the force and its point of application, which is called the center of gravity. The statement is true or false. Okay. So the hydrostatic forces act along the center of gravity, it is stating. So is it true or false? Yeah, exactly. So this is false because the hydrostatic forces will act along the center of pressure. Okay. I think this is already repeated, so we can skip it. Next question is, on a floating body, buoyant forces acts at the center of the floating body, center of gravity of the floating body, center of the fluid vertically below the body, center of the displaced fluid. Okay. So what would be the answer? Floating body. Okay. Again, option D, correct. Right. So floating body, the buoyant forces actually acts along the center of the displaced fluid and not the center of gravity of the object. Okay. Next question is, for a completely submerged body with center of gravity G and center of buoyancy B, the condition of stable equilibrium will be that G needs to be located below B. Is it true or false? Completely submerged body. Center of gravity must be below the center of buoyancy. So is it true or false? We just discuss it. I don't think that's very complicated. True, correct. So if you recall, we saw that if the center of gravity is below the center of buoyancy, then this kind of configuration for submerged bodies will generate a restoring couple that would oppose the displacing couple and restore the body back to its equilibrium position. Okay. So this is the question. This is a question that you might need to use pen and paper to solve. Okay, it is an extensive problem, so let us look into it. Okay, a sector plate is provided on a water spillway as shown in the figure given below. Assuming G is equal to 10, density is 1000 kg per meter cube, the resultant force per meter length of the plate of the gate will be, okay, so if you see that, sorry, the fluid is kept at this location. Okay, so this is the gate. As I already took an example, it's a semicircular half cylinder shaped gate, and of course there is no fluid in this region. Okay, but I already told you how to find the net forces. So that it's not even cylinder. Okay, it's again, the details are already mentioned here. So actually it makes an angle of 60 degree and not 90 degrees, so it's not even a complete cylinder. Okay, so this is the given shape under consideration. So now you need to find the net force that acts on the plate. Okay, so we need to find the vertical force and the horizontal force components. Try it out. I will give you 7 minutes, I guess that is ample amount of time. Try it out. Okay, so you need to find the, first of all, for vertical force, it will be the weight of the fluid that is being balanced in this region of the gate. Okay, so you need to find the volume. The again the tricky part will be to find the volume of the fluid in this region. Okay, it's not a semicircle, so it's actually a sector of angle 60 degrees, so you need to find accordingly the corresponding area and the volume. So find the volume of the fluid in this region to find the net vertical force, and then again the projection of this area to find the net horizontal force. Okay, so that would be your task. So I'll give you say 7 minutes, maybe by 7:46 you can give me an answer or update. Okay, so try it out. Okay, so never, it's like no problem, it's completely fine. Again, I think like our discussions today were quite extensive, given that of course the topics to be needed to be covered was quite large, so we didn't have enough time to give for solving the problems in the problem solving session, so sorry for that. But let's just try to look into the solution. Okay. And I know, like, given enough time, it would have been easily solved by everyone, so but still let us look into it. Okay. So so the net horizontal forces is actually easy to find, because we know that the projected area will basically be a rectangle of, say, length this and breadth, say, b. Okay, and but since it is asked to find the net force per unit width, right, so we can consider this to be, say, 1 to simplify our analysis. So our task was to find the value of this length. Okay, so the radius is b. Okay, AD is so AO is 5 and OB is 5. So since this angle is 30 degree, so this I will say say C. Okay, then AC is again easy to find, because say if we use AC by AD would be sine 30 degree, correct? So AC would be AD times sine 30 is 0.5, or AD is 5, so 5 times 0.5 is equal to 2.5. Okay, so that's how you find. So if this is 2.5, this is again from symmetry, this is 2.5, so 2.5 to 205, so AB is 5, so you know that the area would be 5 times 1. Okay, again H bar would be distance from the free surface to this point, to the center, so again this would be 2.5. So rho is 1000, G is 10. Again, I feel very sorry that you are asked to take G as 10, but unless and until given, you should take G as 9.81. But since it's explicitly given in this problem to take G as 10, so you take G as 10. H bar is 2.5 and A is 5, as I already found out here. So Fx would be, or force, horizontal force would be 125 kilonewton per unit width. Okay, the more complicated task was to find the net vertical force, that is to find the weight of the fluid engulfed within this region. Okay, so we already discussed how the hydrostatic force is evaluated for curved surfaces or curved hollow surfaces. So we assume that this curved hollow surface engulfs a fluid of this shape. Then we need to find the net mass of fluid or weight of fluid in this particular region. So we need to do that, need to first find the area of this particular region. Okay, so for that you'll see that the area can be found out as, or the volume would be area times 1, because we are asked to take per unit width. Okay, so we'll take the width as 1. So area would be the area of this particular sector, say A, B and O, minus the area of this triangle A, B and O. Okay, I'm sorry, let us say give it a name, say G, that would be better. So area of the sector AGBO and minus the area of the triangle ACBO. Okay, very sorry for the naming, but this is how we proceed. Okay, so area of sector would be is found by the area, the angle, that is the angle of the sector, that is angle covered by a sector, this theta in this case is 60 degree, theta by 360 times pi r square minus area of the triangle half times base times height. Okay, theta is 60 degree, pi is 3.1416 and r is 5, minus half is base is, your base is 2.5 2.55, and height would be 5 times cos theta. Okay, so 5 cos 30, that is theta is 30, is 5 cos 30. So if you do that, you will get V as 13.09 minus 10.825 or 2.265 meter cube. Okay, and we are also considering 1 here per unit width. Okay, so volume is 2.265 meter cube. Then Fy would be rho g times volume. So rho is 1000, g is again 10, asked to be taken explicitly in this case, and V is 2.265 or Fy is 22.65 kN. So if you find the resultant force, you will get Frs square root of Fx square plus Fy square, or 112 square plus 22.65 square, or Fr is 127.03 kN. Okay, I hope this is clear. So if you look into the options, so sorry, 127.03, it's not optional, so the correct answer is none of the above. Okay, none of the above. So let us look into the next question. I think that can be the last question for today's discussion. Okay, so yeah, let us consider this example. Oh no, I think I skipped that part. Okay, sorry for that. Okay, let us just, I will take the example. Okay, anyways, for the sake of saving time, I think I can take this example. Okay, sorry for that. Okay, I forgot to add that question here. So okay, so the task is again similar to what we have discussed previously. We have taken an example. If you remember, we took the example of a semicircular shaped gate. Okay, so similar configuration, but now rather the first change is that your surface is now at an angle theta. Okay, and it's a rectangular plate. So again, the analysis of the forces becomes simpler because we do not need to especially do the integration part, so it becomes a bit more simpler. So task is similar. We need to find the value of force P that needs to be applied in this particular configuration so that the gate does not open. Okay, so that's the basic understanding. Okay, so for sake of saving time, I'm sorry that it's already about to be 8, and let us, I think it will go past 8, say by 8:02 or 8:03, but just we also started a bit late, sorry for that, but for the sake of saving time, I'm just quickly go through the example myself. Okay, so if there's any doubt in between, you might ask. Okay, but let us try to solve it. Okay, so this is a geometry. Okay, simple. This is the plate. Again, I'm sorry, plate of length L. Okay, and the free surface is at the height of h, small h. Hinge is at point B, and its plate is placed at the angle of theta. Okay, and let us say the center of pressure, say YCP, because since this is not placed vertically, so it will be a bit different, but still we can understand that if say L by 2 is the center of if L by 2 is the center of your flat plate, then the center of pressure would be at a distance lower than your center of gravity of the particular plate. Okay, so let us consider that YCP is a distance lower than say L by 2. Okay, so if that's the case, then from the hinge that is at point B, the distance of the center of pressure would be L by 2, that is L by 2 minus YCP, correct? Right, so if we consider our axis such that the y-axis is along the plate and x-axis is along vertical, is at a perpendicular direction above the in this direction perpendicular to the plate, then your distance r would be the distance of L by 2 minus YCP. Okay, so this is the distance of your application of center of pressure from the hinge. Okay, so now the net force that acts along the centroid of AB, the net force because of the water that acts along the centroid of AB, okay, actually along the center of pressure, would be net force is rho g times area times h by 2. Okay, so if you remember, the depth does not depend upon the configuration, so it just irrespective of the orientation, it only depends on the vertical displacement. Okay, the pressure force only depends on the vertical displacement, not the horizontal displacement. So you might ask, why not h by 2 sine theta? Okay, it's not the case. If you remember from the Weygnaud's theorem, the net vertical force always depends on the net pressure force always depends on the net vertical distance from the free surface. Okay, that's why since the vertical distance is h by 2, okay, h by 2, that's why your net pressure force would be rho g h by 2 lb. Okay, so that's your net pressure force. Now you need to find the expression for center of pressure. Okay, so that's first of all you need to find the center of pressure. So to do that, we again take the aid of the Weygnaud's theorem from the notes, if you remember. So f times ycp would be equal to integral of ydf. Okay, so, or again, I will not go back how we got into this formula. You can just get back to the notes to see this relation. Okay, just apply that. From that, then you will get f times ycp is equal to rho g sine theta ixx. Okay, you need to find ycp to evaluate the net moment. Then you will do a net moment balance between the force acting along the center of pressure and this force p. That's why you need to find ycp. Okay, so now we have to find the expression of ycp. Then we will have rho g sine theta times ixx. Okay, then ixx is bl cube by 12, because if this is the say the plate and we consider the width to be say b. Okay, I took it w here, but let us take b because in derivations I took it as b. So let us take the width as b. Then the moment of area moment of inertia of the plate along the x axis would be bl cube. L is the length of the plate by 12. Okay, it's a rectangular plate. So ycp would simply be rho g sine theta bl cube by 12 times the force F, and F, if you recall, is given by rho g h by 2 times lb. Okay, so ycp is simply then substitute the value of F in this expression, then you will get ycp as L square sine theta by 6h. Okay, I'm sorry if I'm rushing a bit, but I think it's a simple substitution, so you can easily do it. Okay, I will share the notes eventually, so you will get to know how it was derived. Okay, then we know that now since we already got the expression for ycp, now we just need to do a moment balance. Okay, so now we can see why we had to take the aid of the Weygnaud's theorem. Okay, so from this we could find the value of ycp. Now since ycp is known, just substitute the value of ycp here. Now then do a moment balance across the hinge at b, then you can find the net value of p. So p net moment balance would basically be p times L, p times this distance L is equal to your pressure force F times R, where R is L by 2 minus ycp. Okay, so that's what we'll basically do. See, p by L is equal to p times L is equal to F by R, where or F times L by 2 minus ycp. Ycp is L square sine theta by 6h. Okay, then just substitute the value of your F in the expression, so you will get p times L is equal to, just simplify this expression. Okay, I am not doing it for now, just do that. Then you will get PL is equal to rho g L square b times 3h minus L sin theta by 12. Now since L sin theta is 2h, if you go back to this diagram, sorry, L sin theta is equal to h. Okay, if this is L and this is theta, then L sin theta is equal to h. Just substitute that value here, then you will get p is equal to rho g lb times 2h by 12, or if you simplify it further, or you will get p as rho g lbh by 6. Now if you substitute the value of L, B and H, rho is 1000, G is 9.81, L is 3, B is 8 and H is 1 given in the problem, then you will get P as 39.24 kilonewton. Okay, so any doubt in this particular problem? Okay, if you want I can repeat any portions if you want, but any doubt in this particular problem? the logic, I want to know if there's any doubt in logic, because the derivation and the substitution part is quite simple. Just substitute the expression, you will get the result. And I will also share a note, so there should not be any confusion in that regard. But any doubt in the logic? Okay. So I hope if there's no comments, then I hope the doubt is there's no further doubt. Okay. So for the same regard, I think I will just take one more example in the next class regarding the same, to just compensate the loss of time today, because unfortunately or fortunately today's discussion was a bit more extensive than compared to previous sessions, because a lot more topics were discussed. So sorry for that, but I'll definitely cover that part in the next lecture, just next session, just to compensate the co- concepts that were not covered in today's part. Okay, just one example. Okay, so I hope this is all right. Then if that's all, then I think we can end today. Okay, then let's all meet in the next class. Okay, in the next week. Okay, and if there's any doubt, you might please ask in the next class as well. Okay, for today, yes, its time is already past 8, so I think I will end it here today. But if there's any doubt, you can ask in next week or in the discussion forum. Okay, discussions are always welcome. Okay, so okay, then if that's the case, then let's end here today, and thank you everyone. Okay, I'll end the class.